In chapter 10, we shall learn about some applications of differential geometry. In our first module of this chapter, we shall learn about the applications of tensors in physical laws and equations. First of all, we shall learn about the tensorial approach or tensorial form of Maxwell's equations, which is a very important equation in the field of electrodynamics. Maxwell in 1861 published a paper where he has given 4 equations on electrodynamics. Here we shall learn about the solutions of this Maxwell's equation in tensor form, and secondly we shall study the energy momentum tensor. Energy momentum tensor is also a very important concept in the field of physics as well as in mathematics. It is applied in general theory of relativity, in hydrodynamics and many fields. So, energy momentum tensor is a very important concept in physics and also in mathematics. Einstein 100 years ago in 1915 established a relation between energy momentum tensor and the space time curvature. Here we shall see about these concepts and the deductions of energy momentum tensor for n dimensional space and the relation between the energy momentum tensor and the space time curvature given by Einstein. In chapter 10, we shall learn about some applications of differential geometry. In our first module, we study the applications of tensors in physical laws and equations. Here we have 2 learning objects. First one is electromagnetic field tensors and the second one is energy momentum tensor. Now, electromagnetic field tensors is obtained from the Maxwell's equation, where we have 2 fundamental quantities E and H, that is electricity field and the magnetic field, and the electric state of the matter also related to electric charge density rho. So, rho is the electric charge density and the current density is denoted by J. So, Maxwell's given the equations in 1861, del dot E equals to 4 pi rho, del dot H equals to 0, del cross E equals to minus 1 by C del H del T, del cross H equals to 1 by C del E del T plus 4 pi by C J, where J equals to rho V. So, V is the velocity of the electric charge and C is the velocity of light and del is the Nabla operator. Now, actually these Maxwell's equations are the relation between the electric field, the magnetic field and the velocity of light. These are the system of 4 differential equations, rather partial differential equations, and the solutions of this set of equations from 1 to 4 will give E and H in terms of a scalar function f x y z t and a vector field A x y z t, because we are in the 4 dimensional. So, the solutions will have the functions of 4 variables x, y, z and t. Now, let the covariant form of the 4 vector has components a I, and the curl of a I is denoted by f I j. So, we know from our tensor calculus that a I comma j minus a j comma I is the curl of a I, and that is equals to f I j. And we have also obtained this expression that f I j is del a I by del x j minus del a j by del x I. So, as an exercise we have done this relation previously. So, curl a I is f I j and it is a skew symmetric. So, f I j equals to minus f j I. Now, this f I j is called electromagnetic field tensor. So, it is a covariant tensor of rank 2 and it is a skew symmetric tensor. We know that a skew symmetric covariant tensor of rank 2 has n minus 1 by 2 independent components if the dimension of the space is n. So, f I j also has n minus 1 by 2 independent components. So, if the dimension is 4, f I j has 6 independent components. Now, solving in terms of E I and H I from 1 to 4, we have E I equals to minus del f del x I minus 1 by c del a I del t, where I is running from 1 to 3. That means, we have taken x as x 1, y as x 2 and z as x 3 and t as x 4. So, in the equation we have just kept the t as it is, and the first expression, that is del f del x I. So, del x 1, del x 2, del x 3 will be there. So, E I have this expression. Now, as A I can be expressed in this form G I j A j. So, it is the inner product of G I j and A j. So, in 4 dimensional Minkowski space, we know that the metric is this one, d s square equal to minus d x square minus d y square minus d z square plus c square d t square. That means, we have G I j equals to minus 1 for I equals to j equals to 1 to 3 and G 4 equal to c square, and otherwise when I is not equal to j, G I j is equal to 0. So, A I has the components minus a x, minus a y, minus a z and f. So, E 1 can be written in this form minus del a 4 by del x 1 plus del a 1 by del x 4. That means, we can write it in this form f 1 4. Similarly, E 2 can be expressed as f 2 4 and E 3 as f 3 4. So, in general we can write that E I can be expressed in terms of f I 4, where I is 1 to 3. Again, H x, that is the magnetic field tensor, can be expressed in this form del A z by del y minus del A y by del z. So, if I express in terms of f I j, H 1 will be equals to f 2 3 Similarly, H2 can be written as F31 and H3 can be written as F12. Thus, we can write Hi equals to Fjk, where Ijk equals to 1, 2, 3 and it moves cyclically. That means, we have expressed Ei, that is the electric field, and the magnetic field Hi in terms of Fij, that is the curl of Ai. So, 6 independent components of Fij of the electromagnetic field tensor completely give us the information about the electromagnetic field described by the electric and magnetic field strengths E and H. So, we have expressed the electric field and the magnetic field as a solution of the Maxwell's equation in the tensor form, which is the curl of Ai in terms of curl of Ai. In first section of module 1 of chapter 10, we have learned about the electromagnetic field tensors, where we have obtained the solutions of Maxwell's equation in terms of tensor form. In the next section, we shall learn about energy momentum tensor, a very important concept in the field of tensor. Energy momentum tensor is applicable in the field of general theory of relativity, hydrodynamics, electromagnetic field theory, and in various physical laws. Energy momentum tensor is divergence free, and we shall see this one, that divergence of the energy momentum tensor is 0. In 1915, that means 100 years ago, Albert Einstein established the relation between energy momentum tensor and space time curvature in the theory of general theory of relativity. Here we shall discuss about these things, and we shall also obtain the field equation for empty space time. Empty space time means there is no other field except the gravitational fields. So, let us study the energy momentum tensor in this section. So, in this section we shall learn about energy momentum tensor. Now, in the field of electromagnetic theory, hydrodynamics and general theory of relativity, the energy momentum tensors play very important role. Now, if mu 0 is the proper density of the matter and Vi is the velocity vector, that is dxi dt, then the energy momentum tensor Tij is defined by Tij equals to mu 0 c square Vi Vj, and mu 0 c square is expressed as mu. So, Tij can be expressed in the form of mu Vi Vj, the c is the velocity of light. Where Tij is the flow of ith component of the 4 momentum along the jth direction, and Tij are the components of contravariant tensor of rank 2. Now, the different components of Tij have different meanings. For this one, T44 is the energy density, it expresses the energy density. Tij is the flow of ith component of momentum per unit area in the jth direction, and Tii is pressure across the ith plane. So, these are the different meaning of Tij's. Now, if we take the covariant derivative of this Tij, we get this one Tij comma k equals to del Tij by del xk plus gamma I mk Tmj plus gamma I lk Til. So, these gamma I mk, gamma j lk are the Christoffel symbols of second kind. And this is the covariant derivative of Tij with respect to xk. Now, if we contract this expression for j equal to k, and as covariant derivative of Gij is 0, by Ricci's theorem we know that the covariant derivative of Gij is 0. So, we have Tijj equals to 0. That means, in the absence of matter, the energy momentum tensor vanishes, and also the divergence Tijj vanishes at all points. So, it follows from 13 that divergence of Tij is 0. Now, Einstein in 1915, that is 100 years ago, identified this energy momentum tensor as a source of the space time curvature. Now, space time curvature means in general theory of relativity, it is assumed that space time is curved by the presence of matter, or we can think about it as energy, and this curvature being represented by Riemann tensor. And he has given the relation Rij minus half Rgij equals to k Tij, where r is the small r is the scalar curvature of the space, Rij is the Ricci curvature tensor, and Gij is, we know that is the metric tensor. So, which is the relation between energy momentum tensor and the curvature of space time, and just I have told that what is Rij and r. And this can be also written in this form, Rij minus half Rgij is expressed as Gij, this term is taken as Gij. So, we can write this one is called Einstein tensor. So, we can write Gij equals to k Tij, and k is some scalar constant, and whose magnitude determines the effectiveness of the energy density involving the space time. So, we can write Gij equals to k Tij. But this Tij are the covariant form of T upper ij, that is the contravariant part. So, this is the covariant part of energy momentum tensor Tij. Now, energy momentum tensor for perfect fluid, that means a fluid that can be completely characterized by its rest frame mass density and isotropic pressure, that means the pressure is equal in all respect, is defined by Tij equals to mu plus p Vi Vj plus minus p Gij. So, this is the energy momentum tensor for perfect fluid. where mu is the scalar quantity known as the rest frame energy density and P is the scalar quantity which is rest frame pressure, and it serves to specify pressure in every direction. So, this energy momentum tensor is given for a perfect fluid. Now, a mechanical medium which have no shearing stresses and where the normal stresses are isotropic, that is all spatial directions are equivalent, is said to be perfect fluid. And now multiplying by Gij and using the fact that Gij equals to 4 because we are in 4 dimensional space. So, we get Gij Rij minus half R Gij equals to K Gij Tij. Now, from here we get that minus R equals to K T, because Gij and Tij, if we just contract, it gives T, and Gij Rij will give the scalar curvature R, and Gij will give 4. So, simplifying this relation, we get minus R equals to K T. That means, the value of K is equal to minus R by T. So, if we replace this value in 14, we get Rij equals to R half Gij minus 1 by T Tij. Or simplifying this one, we get Rij equals to R by 2T Tgij minus 2 Tij. So, this is the expression for Ricci tensor in terms of the covariant form of energy momentum tensor. Now, if Tij equals to 0, that means energy momentum tensor vanishes, then T will be also equal to 0, and in that case equation becomes this one, that Rij equals to 0. Now, this equation is the field equation for the empty space time. That means, there is no matter present and no physical fields are there except the gravitational field, and for empty space time we have the field equation is Rij equals to 0. Now, the gravitational field does not hamper the emptiness of the space, and so the space between the planets in the solar system can be considered empty as a good approximation where 17 can be applied. So, for very larger calculations, we consider the space between the solar system as a empty space where only the gravitational fields are there, other fields are not present in that case. So, in the first module of chapter 10, we have learned some applications of differential geometry, rather some applications of tensors in physical laws and equations. We have derived the solutions of Maxwell's equation in tensorial form, and next we have defined the energy momentum tensor and obtained that it is divergence free for every point, and also you have seen that energy momentum tensor and the space time curvature are related, which was given by Einstein in 1915. And lastly, we have seen the field equation for empty space time. So, with this we end this module.